again. Happy whatever day it is you're watching this. Today what we're going to do is review rewriting radicals. So that means simplifying radical expressions and being able to simplify if there's operations in there as well, such as multiplication, addition, or subtraction. Alright, so when we rewrite radical expressions, what I want to show you guys first is we can go back and forth between using radicals and using exponents to show, to simplify these radicals or exponents. So, we can always rewrite a radical expression if we have, this is a little difficult to see, but that's n root x to the a. You can rewrite as an exponential expression by saying you have x to the a, but that a is in a fraction over your n root. Alright? So, here we've got a radical form. We've got the fourth root of x squared. Alright, and here they've separated it now using parentheses, saying that it's saying the fourth root of x squared. Same thing. If we were to put that in exponential form, we would have x, our power a goes on top, so 2 over our root of 4 goes in the denominator. So we have x to the 2/4. And a lot of you guys can simplify that, which would be really just x to the 1/2. Alright? And you guys may know that x to the 1/2 is really just written as the square root of x. Because your x has an invisible power of 1. There's an invisible 1 there in the exponent. And a square root, if you don't see any index, any root in front of your radical, then that means it's a square root, meaning your root is 2, your denominator is 2. Alright, what if we went backwards? We've got x to the 3/4. X to the 3/4. So if we put this in radical form, what is our root? It's the fourth root, so I would have a 4, an index of 4 right there in my radical, and then my x is to what power? It's to the third power. Alright, what if I've got x to the 2/5? My root, my index for the radical is 5, and then my power for the x is 2. Alright, if I've got the 5th root of x, then that means if I put it in exponential form, I'm going to have x. What's the power of my x? How many x's do I have here? Just 1. This is x to the 1st. So x to the 1 over my root, which is 5. Alright, so we can go back and forth between radical form and exponential form to help us simplify these radicals. Now, none of these radicals could be simplified, so now we're going to take a look at some radicals that can be simplified. Alright, so right here, when we're working on rewriting these radicals, we're going to start with this simple one. Square root, because there's no index here, the square root of 36 x to the 6th. Alright, so something that might help is if you separate this. Alright, if you separate it into the square root of 36 and the square root of x to the 6th. Alright, now what I've found is that on these, I can just leave it in radical form because a lot of times our brains can work those numbers a lot easier than having it in exponential form, like 36 to the 1/2. But with this, I'm going to change this to exponential form so you guys can see an easy way to simplify it. Now, we'll start with the number. Square root of 36. Do we know what that is? Yeah, we know that it's 6. If you weren't sure about that, you can always break it down by putting 36 in a box. There's other methods as well, but we've focused on the upside down cake method in class. And a prime number that goes into 36 is 2. 2 goes into 36 18 times. 2 can go into 18 9 times. 3 goes into 9 3 times. And 3 goes into 3 once. Once you hit that candle to your cake, you're going to circle pairs on the outside. And I have nothing left over, so that means this square root of 36 ends up just being 6. Like no radical, just the number 6. Alright? Now with this guy, I'm going to change this guy to exponential form. So this is x to the 6th over my root. This is a square root, right? So over 2. So I'm going to simplify that fraction. What's 6 divided by 2? It's 3 with nothing left over, right? So that is really x to the 3rd, and I also have nothing left over. So my final answer here is going to be just 6x to the 3rd with no radicals, nothing. That's how we would simplify it. Alright, so let's take a look at another example. How about this one right next to it, where we have the square root of 8, x to the 7th, y to the 9th. Again, we're going to split this up. So we're going to have radical 8, we're going to have radical square root of x to the 7th, and then square root of y to the 9th. Alright, so I'm going to start with this 8 first. Now, is 8 a perfect square like 36 was? No. So what we're going to do is we're going to use that upside down cake to break it down. What's a prime that goes into 8? 2 can go into 8 4 times. What's a prime that goes into 4? 2 goes into 4 2 times. What's a prime that goes into 2? 2 goes into 2 once. I can circle this perfect pair, but then I have this leftover right here. So that means this square root of 8 simplifies to I have one pair of perfect 2's. So that one pair goes on the outside of my radical sign, and then this leftover goes back in my radical. So the square root of 8 really simplifies down to 2 radical 2. Alright? So we're going to have that there. Then I have this square root of x to the 7th. So like what we did before, we're going to put this in exponential form. So I have x to the 7th, and then the root was 2, because this is the square root. Now here, 7 over 2, if I put that as a mixed number, 2 goes into 7, 2 goes into 7 3 times with 1 left over, right? So that means 3, and then we've got 1 left over. So 7 over 2, 7 halves, is 3 1/2, right? So the way that we would write this is this x cubed is whole. So that would go outside, I'm going to put it right here, outside of a radical, but since we had leftovers, we had 1 x that was left over. So we've got an x to the 1st that has to go back underneath the square root sign. Alright, then with the y to the 9th, we do the same thing. Y to the 9th over 2, and that as a mixed number is going to be y to the 4 1/2. So guess what that's going to look like? That's going to be y to the 4th, and then 1y left over in the square root sign. So, putting all this together now, I've circled the parts that we're going to be putting together. We've got a 2 x cubed and a y to the fourth that are all on the outside of our radical sign, of our square root sign. So we're going to have 2x cubed y to the fourth. And then we have these other things that were left over inside our square root sign. So then I'm going to have the square root of, I had a 2, an x, and a y that had to go back underneath the square root. So 2x and y. And there's our final answer. Alright? Now, what if you had a different index, a different root? Like here, this was a square root, but here we've got a cubed root. Guess what? It's going to work the same way, but this time our denominator in our exponent is going to be 3, because that's our root. So if I split this up, we're going to have the cubed root of x to the 7th, the cubed root of y to the 5th, and the cubed root of z to the, oh, that's a z, not an x, z to the 3rd. Alright, sorry, you guys didn't even see that. So, again, put this in exponential form. So this is going to be x to the 7 over 3, and then put it as a mixed number. 3 goes into 7 twice. So this is going to be x to the 2 and 1/3. Alright, because 3 goes into 7 twice, making 6, and then there's 1 left over. So this is really going to be x squared, and then we have a cubed root with 1x left over. Alright, with our y, we're going to have y to the 5 over 3, and as a mixed number, that's y to the 3 only goes into 5 once, with 2 left over. So this time, y to the 1 is really just y. Y to the first is just y. And then our root is 3. But inside, we have 2 y's that are left over. So this is going to be y squared left over inside of there. Alright, and then for z, this is going to be z to the 3 over 3. And 3 over 3 is just 1, right? Z to the first. And z to the first is just z. Alright, so now when we put all this together, we're going to start with the stuff that is on the outside of a radical. So we have this x squared, we have this y, and we have this z. Alright, so this is going to be x squared y z, and then remember everything that's left over is in a cubed root. And our leftovers here are an x and a y squared. So we've got x and y squared. And there's our final answer. Alright, does that make sense, guys? So, that's simplifying these radical expressions. Now, what if we throw operations into there? For example, let's try, let's do number 27 right here, alright? And then we'll take a look at 28. So, we've got the square root of 6x squared times the square root of 4x cubed. Now, when we multiply things, we can just multiply these straight together. Alright? Just put it all into 1 and then break it down. Alright? So, and that's when we're multiplying. Since all of this is in a square root and all of this is in a square root, that means my whole thing is going to end up being in a square root. Alright? And 6 times 4 is 24. 6 times 4 is 24. Alright? And then we have this x squared times x cubed. X squared times x cubed. We're going to be adding these exponents, so this is going to be x to the 5th. Alright? We can only multiply these if they are the same index. Otherwise, we would have to get a common index, a common denominator, and it's a little bit more work. So we're just going to be focusing on when these are the same index. Now that we've multiplied these together, we can simplify this, just like what we did before. So this is like saying we've got the square root of 24 and the square root of x to the 5th. Okay, so the square root of 24, I'm going to put in the upside down cake. 2 goes into 24 12 times. 2 goes into 12 6 times. 2 goes into 6 3 times. And 3 goes into 3 once. Alright, so now what we can do is circle those perfect pairs. I just have one pair of 2's and then a 2 and a 3 left over. So this 24 is really going to be 2 radical 6, because the 2 and 3 get multiplied back together. Alright, and then this x to the square root of x to the 5th is x to the 5th over 2, which is x to the 2.5, which we can write as x squared, and then the square root of just 1x left over. So, putting this all together, we have this 2 and this x squared on the outside, and then we have this 6 and this x on the inside of our square root. Alright, and there's our final answer. So, similar idea when we have numbers on the outside of our square root. Multiply everything together. So this 12 and this 2 are on the outside, so that's what I'm going to multiply together. If nothing were on the outside of this radical 9x, then I wouldn't have to multiply anything by the 12. I would just leave 12 on the outside and it'd be fine on its own. But I'm going to multiply together this 12 and this 2 to get 24. And that's already on the outside of our square root sign. Everything else is on the inside of our square root sign. So now we're going to take this 6 and this 9 and multiply them together. And 6 times 9 is 54. And then this x times x, which is x squared. So, since this 24 is already on the outside, I'm just going to let it hang out. So we've got this 24 here. I'm just going to circle it because that's going to be part of our answer. Then I've got this square root of 54 and this square root of x squared. So we'll start with this 54 by breaking it down. What's a prime number that goes into 54? It's even, so 2 can go into 54. Let's see here, 27 times? What's a prime that goes into 27? 3 can go into 27 9 times. 3 goes into 9 3 times, and 3 goes into 3 once. Alright, so now I'm going to circle the pairs that I see, and then I've got these guys that are left over. So this square root of 54 really simplifies to 3, that perfect pair of 3. Just one pair, so that's why I only write it once. And then the singles get multiplied back together, so 2 times 3 is 6. And then this square root of x squared, we're going to get x to the 2 over 2, which is x to the first, which is really just x. Alright, so now everything that's on its own on the outside of a radical, I can put together. So I'm going to take this 24 times 3 times x. So 24 times 3 is going to give me 72. And then that x also did not have a square root sign. But I do have a square root 6 that I need to tag onto there. And there's my final answer. Alright. When we are adding or subtracting radical expressions, they must have identical pieces. Like identical, just like if we were doing 7x minus 3x, we can subtract those because they're like terms. If we had 7x squared minus 3x, we wouldn't be able to subtract that because one of our terms has an x squared and the other term is just an x. So same thing when we're adding or subtracting radical expressions, we need to have like terms in order to add or subtract. So for number 34 here, we have 7 and the cubed root of x. We have 3 and the cubed root of x. These are like terms, so we can subtract this. And when we subtract, all we're doing is subtracting the coefficient in front. Alright, so because these guys are like terms, that means all we need to do is take this 7 minus this 3. And 7 minus 3 is 4, correct? So this is just 4, and then the term, just like if you were taking 7x minus 3x, you would get 4x. So 7 cubed root of x minus 3 cubed root of x is 4 cubed root of x. Okay? There's your final answer on that one. Now, sometimes, like on this one over here, they don't look identical right off the bat, right? So we have to simplify first to see if we can make them identical. Alright, so here we've got this 5 and the square root of x to the 4th. Alright, this 5 we can't really do anything about, but this square root of x to the 4th, we can try to change that. Alright, so this square root of x to the 4th is really x to the 4th over 2, right? And 4 over 2 is just 2. So that's really just 5x squared. Alright, so I'm going to go ahead and write that down here. This 5 is already all by itself. And then this x squared, this square root of x to the 4th, we simplified down to x squared. So this is really just 5x squared. There were no leftovers, no remainders, so that's why we don't have a radical sign. Same thing. On this other one, we've got this 6 all by itself. And then if we try to break this down, this cubed root, x to the 6th, this is going to be x to the 6th over 3, because 3 is our root, our index. 6 divided by 3 is what? Hey, 2. There's no leftovers there. So that means this is really 6x squared. And then what sign is in between there? A plus sign. Are these like terms? Yeah, they are. So we're just taking 5x squared plus 6x squared, which is what? 11x squared. Alright. Take a look at one other example. Right here, I've got this 7x and then the square root of x. Alright, and then minus 2, the square root of x cubed. So, if we take a look at this, if I put this 7x is already on the outside, so I'm not going to worry about that right now. This square root of x. Can I simplify that? if I put it in exponential form, this is x to the first, and then in the denominator we'd have a 2, because this is the square root. That's our root. So I can't simplify that. I would leave it just as 7x square root of x. Let's see if we can simplify this one though. So the 2 I'll leave because it's already on the outside. For this guy, I've got x to the third over 2, because this is a square root. There's no index there, meaning it's a square root. And that 3 over 2 is really 1 1/2. So 1 1/2. And we can rewrite that as x to the first, which is just x, and then I have 1x left over, like this. Alright, so instead of this guy right here, I can rewrite it as this is really 7x square root x minus 2, and instead of that square root of x squared, x cubed, I can write x square root x. Do these have like terms now? Yeah, both of these coefficients have the terms x square root of x after it. So, really, all I need to do is take 7 minus 2. Alright, so that's going to give me 7 minus 2 is 5, and then leave the like term after it. So x square root x. And there's my final answer. So there's the basics of simplifying radical expressions. If you guys have any questions, feel free to reach out to me and ask, or there's lots of other resources that I'm sure you guys can find as well. So if you have any questions, get the help that you need. Alright, I will see you next time.